Hello everyone. So in this video lecture we will look into the precipitation process, how actually precipitation or the rainfall starts from a cloud. We all know cloud, it normally adds beauty to the atmosphere, beauty to our landscape or beauty to our sky. But apart from this artistic view, cloud has also some important role because the cloud regulates the Earth's energy balance. Cloud normally regulates the Earth's energy balance because during daytime the cloud normally reflects the solar light or solar radiation and keeps the daytime relatively cooler. So the cloud normally keeps the daytime temperature relatively low, or cloud normally keeps the daytime relatively cooler. Similarly, during night time, the same cloud reflects the infrared radiation to the earth and it keeps the nighttime temperature relatively high. So the presence of cloud keeps the daytime temperature relatively low, or it keeps the daytime relatively cooler, and it keeps the nighttime temperature relatively higher. Apart from this one, we all know that whenever the precipitation takes place or whenever the rainfall takes place, it gives us a very relaxation from the high temperature, or it gives us relaxation from the scorching beat of the sun. Therefore, the rainfall or the precipitation has a very important control on the human being. In addition to this, we all know that sometimes what happens, although the cloud present in the sky for more than 1 month, but not a single drop of precipitation takes place. That means that the cloudy does not always guarantee about the precipitation. The cloudy sky does not always guarantee the precipitation because, as we have already discussed, sometimes cloud may persist in the sky for more than 1 month, but not a single drop of precipitation will take place, and in some other instance the cloud can develop and a huge amount of precipitation can take place within a time frame of less than 1 hour. Therefore, the question comes, why some cloud precipitate and why not others? Why only some cloud initiates the precipitation and why not other clouds can initiate the rainfall process? Now, in order to get the answer for this particular question, we need to look into the average size of the rain droplet as well as that of the cloud droplet. We all know the clouds are composed of huge numbers of cloud droplets, and if we look into the average diameter of this cloud droplet, then it is only 0.02 millimeter. The average diameter of the cloud droplet is 0.02 millimeter, but the average diameter of the rain droplet, the average diameter of a typical rain droplet is approximately 2 millimeter. That means we need 1 million numbers of cloud droplets to combine for the formation of one average size rain droplet. And we all know that this cloud droplet initially forms directly over a condensation nuclei. And the average size of this condensation nuclei is only 0.0002 millimeter. Although this is the basic process of the cloud droplet formation as well as that of the rain droplet formation, but this process is not that much simple and straightforward, because although condensation can initiate directly over the condensation nuclei, but in a normal time it takes approximately 1 month it takes approximately 1 month for the formation of one average size cloud droplet. That means the condensation process has to continue, or the condensation needs to continue directly above this condensation nuclei for a time period of approximately 1 month. Then only a typical cloud droplet will form. But we all know that cloud may form and precipitate within a time frame of less than 30 minutes or less than 1 hour. So this thing indicates that apart from this condensation process, definitely there exists some other process that can initiate the precipitation formation. That can initiate the precipitation formation or precipitation process. Although a very little is known about this initiation of precipitation process, but there are two different processes. There exist two different processes that normally explains the formation or the initiation of the precipitation process. First one is collision coalescence process. Collision coalescence process, it is also called Bowen's process, and second one is your ice crystal process. Ice crystal process, and it is also called Bergeron process. It is also called your Bergeron process. So we have two different theory that explains the precipitation process. First one is collision coalescence process. This is also called your Bowen's process, and second one is your ice crystal process or your Bergeron process. So first we look into the collision and coalescence process. First we will look into the collision coalescence process, or that is also called your Bowen's process. Now for collision and coalescence process to take place significantly in a cloud, so that a cloud droplet as well as rain droplet will form, what we need is the cloud temperature must be greater than minus 15 degrees Celsius. For this collision and coalescence process to take place efficiently, the cloud top must have a temperature of greater than minus 15 degree Celsius, and such clouds are called your warm cloud. Such clouds are called your warm cloud. So this is the first condition we need for the initiation of precipitation through collision and coalescence process. And second condition is for collision and coalescence process to take place efficiently, some droplet must be larger than others. Some droplets must be larger than others. Now these large droplets normally formed directly over the large condensation nuclei. Large droplets normally form directly over the large condensation nuclei. So these are the two different conditions we need for the collision and coalescence process to initiate the precipitation process in a efficient manner. Okay, now we'll see what actually happens in this Bowen's process or collision and coalescence process. So in collision and coalescence process, we have larger size droplet as well as the small size droplet. Now suppose we will consider this particular droplet. Now when this droplet will start to fall towards the earth surface, when this particular cloud droplet will start to fall towards the earth surface by means of the gravity, immediately what happens? A upward directed force will oppose its movement. Again, when this particular droplet will start falling towards the earth's surface due to the influence of earth's gravity, another force will act in the exactly opposite direction, and that will retards the velocity. That will retard the velocity of this falling droplet. I think you all may have now understood that this particular force is nothing but it is the air resistance. It is the air resistance. That means as soon as this droplet will start to fall, the air resistance will not allow this particular droplet to fall, and it will retard the velocity of this particular rain droplet. And the magnitude of this air resistance is again dependent on two factors. First one is size of droplet, second one is speed of droplet, speed of falling droplet. Now first we'll come to the size part. If a larger size droplet will fall, try to understand these things. If a larger size droplet will fall from the cloud towards the earth's surface, then in an unit time it will encounter more number of air molecules. If a larger size droplet will fall towards the earth's surface, then in an unit time it will encounter more number of air molecules in comparison to a falling droplet whose size is relatively smaller in comparison to this particular droplet. Now if this particular droplet is encountering more number of air molecules in a unit time, that means air resistance will be higher. Air resistance will be relatively higher for this particular droplet. That means larger the droplet, more will be the air resistance. More will be the air resistance. Now coming to the speed part. Suppose we have two same size droplet. We have two same size cloud droplet, but one droplet is falling at a higher velocity and another droplet is falling at a very slow speed or at a very low velocity. Now this droplet which is falling at a relatively high speed, that means again in unit time it will encounter more number of air molecules. It will encounter more number of air molecules, therefore the air resistance will be relatively higher. The air resistance will be relatively higher. Therefore, faster the droplet falls, more will be the air resistance. And combinedly, we can write larger the droplet, faster is the falling velocity, more will be the air resistance. Larger the droplet, faster is the falling velocity, more will be the air resistance upon an cloud droplet. Now one more thing. Suppose we have a larger size droplet and we have a smaller size droplet, okay, and both are falling towards the earth's surface. Both are falling towards the earth's surface. Now if we look into the surface area to weight ratio, if we look into the surface area to weight ratio, then the larger droplet has relatively small surface area to weight ratio in comparison to smaller droplet which has relatively high surface area to weight ratio. Now due to this small surface area to weight ratio, this larger droplet, please remember this one, due to this small surface area to weight ratio, this larger droplet will fall faster in comparison to this smaller droplet. Due to this small surface area to weight ratio, this larger droplet will fall faster in comparison to this smaller droplet. Now suppose this is a cloud droplet which is falling towards the earth's surface, okay. Now this particular droplet is falling towards the earth's surface due to the gravity, and this gravity is directed in the downward direction. At the same time, the air resistance is opposing its fall that means the air resistance is directed in exactly opposite direction or in the upward direction. Gravity is directed in the downward direction, whereas the air resistance is directed in the upward direction. But as long as the gravity or the magnitude of this gravity is more than the air resistance, as long as the magnitude of gravitational attraction or magnitude of gravity is greater than air resistance, the speed of this droplet will increase. The speed of this particular droplet will increase, and as soon as or when the magnitude of gravity will be equals to air resistance, the magnitude of gravity is equals to air resistance, at that time what happens, this particular droplet will fall towards the earth's surface, but at a constant velocity, and this particular constant velocity that is attended by a falling droplet after the gravitational value or the magnitude of gravity becomes equals to that of the air resistance, this is called your terminal velocity. This is called your terminal velocity. Previously we have seen that the larger droplet falls faster than the smaller droplet. That means in this region larger droplet will fall faster than a smaller droplet. Therefore larger droplet reaches terminal velocity earlier than the smaller droplet. As the larger droplet falls at a faster rate in comparison to smaller droplet, therefore the larger droplet normally reaches their terminal velocity relatively earlier in comparison to a smaller droplet. Now as the larger droplet will fall at a fast rate in comparison to smaller droplet, at the same time what happens, or during its way, it normally collided with many small droplets in its path, or when this larger droplet will start falling towards the earth's surface on its path, it normally collides with many small droplets, and from there the name of the process derived as collision process. And when a larger droplet will collide with a small droplet, this small droplet will simply merge with this larger droplet. Again I am telling, when this larger droplet will collide with this small droplet will merge with this larger droplet, and after this process the size of this larger droplet will be much more higher, or its size will increase. Okay, but at the same time suppose this is a larger droplet and this is a smaller droplet. Okay, and this smaller droplet has relatively, just 1 minute, and this smaller droplet has relatively higher surface tension. This smaller droplet has relatively higher surface tension. Now due to this relatively higher surface tension, when this large droplet and small droplet will collide, the chance of not merging is relatively high, or when this larger droplet and small size droplet will collide with each other, due to the high surface tension of this small droplet, this small size droplet will not merge with this large size droplet easily. Instead of it, what happens, after colliding it will simply bounce back. It will simply reflect away, or it will simply bounce back. Okay, therefore the second part of the name derived, that is your merging process, merging or coalescence process. Okay, so this is the your collision and your coalescence process. Now apart from this collision and coalescence, and another important factor that also contributes significantly in increasing the size of the droplet is the time or the duration a typical droplet spent in cloud. The duration of time or the duration a typical raindrop spent in the cloud. Suppose this is a cloud mass and a droplet was falling in this manner, and here what happens, suppose it suddenly encounter an updraft. Updraft means a very high velocity wind which is flowing from the earth surface towards the high altitude regions. Okay, now when this particular droplet will encounter this relatively high speed of updraft or relatively strong updraft, and if this updraft is sufficiently strong, then this updraft will not allow this droplet to fall. Instead of it, what it will do, it will either keep it in the suspension, or if the magnitude of the updraft will increase sufficiently, then it may cause the raindrop, or it may cause the droplet to travel towards the topmost part of the cloud, or it will cause this particular droplet to travel into a further high altitude part. Now you can see this droplet, it was leaving the cloud, but due to this updraft, again it is traveling within the cloud, or it is traveling into the cloud. That means this is the total length of time. This particular droplet is spending within the cloud. That means during this time period, by means of the collision and coalescence process, the size of this droplet will also increase. And definitely a time will come when this particular updraft will be unable to hold this droplet, and after this droplet will start falling towards the this particular droplet will start falling towards the base of the cloud as well as towards the Earth's surface. Now, so this is the figure of collision and coalescence process. You can see initially we have many small cloud droplets, and when a large size droplet encounter this small size droplet normally collide and merge with the larger size droplet, and thereby the size of this larger size droplet normally increases. So this is the collision and coalescence process. You can look into this figure that we have already discussed, how the size of a typical droplet normally increase if it will spend more time within the cloud. You can see here the cloud droplet has a size of 0.1 mm, and suddenly it encounters a updraft having a speed of 6.5 meter per second. Now this relatively high updraft will not allow this typical cloud droplet to fall towards the cloud base or fall towards the earth surface. Instead of it will take these typical droplets towards the topmost part of the cloud. But as soon as the size of the droplet will reach 1 mm, this updraft will not able to lift it to a higher position. Instead, it will keep it in the suspension. And if the size of the cloud droplet will increase slightly more than 0.1 mm, then this updraft cannot hold the updraft cannot hold this particular droplet, and instead this droplet will start to fall, and by the time this droplet will reach the earth surface, its size will be approximately 5 mm. So this is the collision and coalescence process. Next is your ice crystal process or Bergeron process. For the collision and coalescence process to take place efficiently, we have seen कि we need a cloud having a cloud top temperature more than minus 15 degrees Celsius. Similarly, the ice crystal process to operate ice crystal process to take place efficiently, the cloud have a temperature. The cloud temperature must be less than freezing point of the water, and this type of cloud are called a cold cloud. This type of cloud are called a cold cloud. In warm cloud, where collision and coalescence process is important in the raindrop formation, in this particular cloud we have liquid water only. That means within this cloud we will get only liquid water. But in the cold cloud we have the coexistence of liquid water as well as ice. Therefore, for Bergeron process to operate sufficiently, the cloud must contains both the liquid water as well as solid water, that is your ice. That means this ice crystal process is important in initiating the precipitation in the mid latitude region and here high latitude region, and the collision coalescence process is important in the precipitation process in the low latitude region, but ice crystal process is important in the mid latitude as well as the high latitude regions. In the warm cloud we have already seen that the cloud is completely composed of liquid water. The warm cloud is completely composed of liquid water. But in case of your cold cloud, as you may expect, in case of your cold cloud, the cloud temperature is less than freezing point of the water. That means definitely this cloud must have composed completely of ice, but this is not the case. Although there exists some amount of ice in the cold cloud, but the number of ice is much more less in comparison to liquid water present in the cloud. In the cold cloud, although we have ice, but in comparison to amount of ice, the amount of liquid water in the cloud is relatively high. How is this possible? Because the cloud temperature is less than 0 degrees Celsius. So now the question becomes how at a temperature of less than freezing the water remains in the liquid state. This is because first one, okay, smaller will be the pure water, lesser will be its freezing point. Smaller will be the pure water, lesser will be its freezing point. We know the average diameter of the cloud droplet is 0.02 mm. That means these cloud droplets are extremely small particle or extremely tiny particle. Okay, that means these are the smaller droplets. Similarly, the cloud are composed of extremely pure form of water. They are not contaminated. The water present in the cloud, they are extremely pure. That means within the cloud we have pure water having a very small amount or having a very small quantity. Therefore, this particular water will not freeze at a temperature of 0 degrees Celsius. Instead, they will freeze at a temperature of much more less than 0 degree Celsius. And in most of the instance, these liquids are normally freezes at a temperature of minus 30 degrees Celsius. And the liquid having temperature less than freezing point of water, the water having the temperature less than the freezing point is called supercooled liquid. So this is the first reason that temperature is although the temperature is below freezing point, but the amount of water is so low and the water is so pure that this particular water will not freeze at a temperature of 0 degree Celsius. Instead, they in most of the case they normally freezes at a temperature of minus 30 degrees Celsius. That means we need a very or extremely low temperature to make this liquid water or to convert this liquid water into the solid form of the water. And the second one, we all know कि the water vapor, that is the gaseous form of the water, normally converts into the liquid form of the water, and this process is called your condensation. And condensation normally takes place or it normally happens over a condensation nuclei, over the condensation nuclei, or water normally needs a tiny particle that is called condensation nuclei for condensation to take place, where this water vapor or gaseous form of the water is normally converts into the liquid form of the water. Similarly, for this liquid form of water to convert into the solid form of water, that is your ice, it also needs some particle. These are called ice nuclei. These are called your ice nuclei, and the abundance of this ice nuclei is very low in atmosphere. Very low in atmosphere. The example of some ice nuclei is the ice particle itself, some bacteria and clay particles. The ice particle itself, some bacteria and clay particles are excellent ice nuclei, but the abundance of ice nuclei is very low in our atmosphere. That means although this liquid water can convert into this solid water, but due to the very low abundance of the ice nuclei, they cannot convert. Instead, they normally prefer to stay in the liquid form. That means we have two different reasons which can explain the presence of liquid water or presence of supercooled liquid water within the cloud. First is that this water can freeze, but they need very low temperature. They need very low temperature. Second one, they can freeze or they can convert into the solid form, but the number of ice nuclei is extremely low. The abundance of ice nuclei is extremely low in the cloud, and due to these two reasons, the cold cloud, although having a temperature less than the freezing point of the water, but it mostly contains the supercooled liquid, or it mostly contains liquid form of the water, not the solid form of the water. Now coming to the Bergeron process, as I have already told, the Bergeron process normally takes place where the liquid water and solid water coexist within a cloud. That means within a cloud we have liquid water as well as solid water or the ice. This is liquid water, this is your solid water. Now I expect you all know that the water molecule can leave the liquid water much more easily in comparison to the ice. The water molecule can leave the surface of this liquid water much more easily in comparison to the surface of this ice crystal. That means if we will be able to see this particular liquid water microscopically, then what we will observe, that directly over this liquid water we have more number of water vapor molecules which are leaving the surface. Not only the water molecules will leave the surface of this liquid, but also exactly same number of water molecules are also returning to this particular liquid droplet, because within the cloud the air is saturated. The air is saturated. Now if we look into the same thing directly over the ice, then we will see, although directly over the ice we have the water molecules leaving the surface, and we have the water molecules returning to the surface, but the numbers of water vapor molecules over the solid ice is relatively low in comparison to the air directly above this liquid water, which is relatively higher. Okay, now as the air is saturated, therefore the saturation vapor pressure over the liquid water is much more greater than the saturation vapor pressure over the solid ice. Due to more number of water vapor molecules directly over this liquid water droplet, the saturation vapor pressure over the liquid water is much more higher in comparison to the saturation vapor pressure directly over this ice crystal. And we all know, as there occurs a difference in the pressure, so water vapor molecule starts to travel from the liquid side to the solid side, the liquid side and to the solid side. And as the water vapor molecules are leaving the surface of liquid, that means in order to maintain the equilibrium, this liquid water will evaporate more and more. This will evaporate more and more, and these newly added water vapor molecules to the ice crystal, they will increase the size of this ice crystal. It will increase the size of the ice crystal, whereas the size of the liquid droplet starts to shrink, or it starts to in smaller in size. That means in the ice crystal process, two things are there, and you may have noticed in the CSR net, every time this question is asked. What is the condition of saturation vapor pressure over the liquid and solid, and whether ice crystal grow in expense of liquid water or liquid water grow in expense of ice crystal. So just remember, in ice crystal or Bergeron process, the saturation vapor pressure over the liquid is relatively higher than the saturation vapor pressure over the ice crystal. And as the liquid water is providing the water vapor to the ice crystal to grow, therefore ice crystal grow in expense of liquid water. So this is the Bergeron process. In the Bergeron process, the saturation vapor pressure over the liquid is greater than the saturation vapor pressure over the solid, and ice crystal grow in expense of liquid water or liquid droplet. Okay, and when this ice crystal forms, it starts to fall towards the earth's surface, and on its way it may come in contact with other supercooled liquid, and upon contact this supercooled liquid will freeze. And this process is called accretion process. However, sometimes what happens, after collided with this supercooled liquid during the falling, this ice crystal may break into pieces. It may break into pieces, and they produce splinter. And this individual splinter, they may again work as a new ice crystal, and the accretion process initiates. And in both the cases, a chain reaction normally starts. And these ice crystals are also called your graupel. That means one graupel can give rise to many other graupels. In some other instance, what happens, by a combination of the many hexagonal size ice crystals, a very beautiful structure is formed, that is called your snowflakes. That is called your snowflakes, which is hexagonal in shape. For example, you can look into this figure. For the Bergeron process, you can see there exist more number of water vapor molecules directly over the liquid droplet in comparison to the above the ice crystal. That means the saturation vapor pressure is relatively higher over the liquid water in comparison to the saturation vapor pressure over the solid ice, and gradually the size of this liquid water is decreasing, whereas the size of the ice crystal is increasing. That means in Bergeron process, the ice crystal grows in expense of the your liquid water. And when this particular ice crystal starts to fall, it may come in contact with many supercooled liquid, which may causes the size of the ice crystal to increase, or it may produce graupel, or it may produce your splinter. And when individual ice crystal, in some instance, the individual ice crystal can combine to produce a beautiful structure or a beautiful pieces of ice, that is called your snowflakes. That is called your snowflakes. And depending on the size of the water droplets that is falling towards the earth's surface as well as the other places, we have variety of types of the precipitation. Okay, if the size of the droplet the diameter of the droplet is more than 0.5 mm, then that is called rain. Whereas if the diameter of the droplet is less than 0.5 mm, that is called your drizzle. If the falling droplet will evaporate, then it is called your virga. Whereas the falling of suspended drops is called your shower. Ice crystal and snowflakes falling from the cirrus cloud is called your fall streak. Snow falling from the cumulus cloud is called your flurries, whereas the intense snowfall is called your snow squall. I think we have left one. This figure. You can see the distribution of liquid water and the ice in a cloud. At the base part of the cloud, we will find only liquid water, whereas in the topmost part of the cloud, we will get only ice, whereas in the middle part we will get the mixture of ice and water. Look into the temperature. This part of the cloud will only contain the ice if and only if its temperature is relatively low, whereas in the mid part of the cloud, although the cloud temperature is less than freezing point, but as we have already discussed, there exist two regions which does not allow the liquid water to convert into solid. It contains a mixture of ice and your water. Okay, thank you, take care.